Universal gravitation. Objectives: universal gravitation. Explain Newton's reasoning about the apple falling from the tree. Explain why the moon doesn't hit Earth. Explain how Newton's theory of gravity confirmed the Copernican theory of the solar system. Describe what Newton discovered about gravity. Describe how the force of gravity changes with distance. Describe the gravitational field that surrounds Earth. Describe the gravitational field at Earth's center. Describe the sensation we interpret as weights. Explain ocean tides. Describe the gravitational field around a black hole. Explain the importance of the formulation of the law of universal gravitation. The big idea. Everything pulls on everything else. Objects such as leaves, rain, and satellites fall because of gravity. Gravity is what holds tea in a cup and what makes bubbles rise. It made Earth round, and it builds up the pressures that kindle every star that shines. These are things that gravity does, but what is gravity? Contrary to what some people think, gravity was not discovered by Isaac Newton. That discovery dates back to earlier times when Earth dwellers experienced the consequences of tripping and falling. What Newton discovered, prompted by a falling apple, was that gravity is a universal force, that it is not unique to Earth, as others of his time assumed. Discover. How does the surface area of a balloon vary with diameter? 1. Inflate a round balloon to a diameter of 8 centimeters. Use a marker to draw a rectangle the size of a postage stamp on the balloon. Do not tie the end of the balloon. Now inflate the balloon to a diameter of 16 centimeters. How many postage stamps will fit in the square you drew? 3. If possible, increase the diameter of the balloon to 24 centimeters, and once again determine how many stamps will fit in the square. Analyze and conclude. 1. Observing. Describe how the area of the square grew as you increased the diameter of the balloon. 2. Predicting. If you could increase the diameter of the balloon to 32 centimeters, how many postage stamps would fit in the expanded square? 3. Making generalizations. How does the area of the square drawn on the balloon surface increase with increasing balloon diameter? 13.1. The falling apple. According to popular legend, the idea that gravity extends throughout the universe occurred to Newton while he was sitting underneath an apple tree on his mother's farm, pondering the forces of nature. This scene is illustrated in 13.1. Newton understood the concept of inertia developed earlier by Galileo. He knew that without an outside force, moving objects continue to move at constant speed in a straight line. He knew that if an object undergoes a change in speed or direction, then a force is responsible. A falling apple triggered what was to become one of the most far-reaching generalizations of the human mind. According to legend, Newton discovered that gravity extends to the moon and beyond while sitting under an apple tree, pondering the falling apple. Newton saw the apple fall, or maybe even felt it fall in his head. The story about this is not clear. Perhaps he looked up through the apple tree's branches and noticed the moon. Newton was probably puzzled by the fact that the moon does not follow a straight line path, but instead circles about Earth. He knew that circular motion is accelerated motion, which requires a force. But what was this force? Newton had the insight to see that the moon is falling towards Earth, just as the apple is. Newton reasoned that the moon is falling towards Earth for the same reason an apple falls from a tree. They are both pulled by Earth's gravity. What was Newton's reasoning about the apple falling from the tree? 13.2, the falling moon. Newton developed this idea further. He compared the falling apple with the falling moon. Newton realized that if the moon did not fall, it would move off in a straight line and leave its orbit, as suggested in figure 13.2. His idea was that the moon must be falling around Earth. Thus, the moon falls in the sense that it falls beneath the straight line it would follow if no force acted on it. He hypothesized that the moon was simply a projectile circling the Earth under the attraction of gravity. Newton's hypothesis. Newton compared the motion of the moon to a cannonball fired from the top of a mountain, a high mountain. Figure 13.2. If the moon did not fall, it would follow a straight line path. If the mountaintop was above Earth's atmosphere, air resistance would not impede the motion of the cannonball. If a cannonball were fired with a small horizontal speed, it would follow a parabolic path and soon hit the Earth below. If it were fired faster, its path would be less curved and it would hit Earth farther away. If the cannonball were fired fast enough, its path would become a circle and the cannonball would circle indefinitely. Newton illustrated this in a drawing in figure 13.3. Both the orbiting cannonball and the moon have a component of velocity parallel to Earth's surface. This sideways or tangential velocity, as illustrated in figure 13.14, is sufficient to ensure nearly circular motion around the Earth rather than into it. Figure 13.3. This original drawing by Isaac Newton shows how a projectile fired fast enough would fall around Earth and become an Earth satellite. Figure 13.4. Tangential velocity is the sideways velocity, the component of velocity parallel to the surface of the Earth and perpendicular to the pull of gravity. Here we have the pull of gravity down and the tangential velocity at 90 degrees relative to the pull of gravity. The moon is actually falling toward Earth, but has great enough tangential velocity to avoid hitting Earth. If there is no resistance to reduce its speed, the moon will continue falling around and around Earth indefinitely. Newton's test. For Newton's idea to advance from hypothesis to scientific theory, it would have to be tested. Newton's test was to see if the moon's fall beneath its otherwise straight line path was in correct proportion to the fall of an apple or any object at Earth's surface. He reasoned that the mass of the moon should not affect how it falls, just as the mass has no effect on the acceleration of freely falling objects on Earth. How far the moon falls and how far an apple at Earth's surface falls should relate only to their respective distances from Earth's center. As illustrated in figure 13.5, the moon was already known to be 60 times farther from the center of the Earth than an apple at Earth's surface. The apple will fall 5 meters in its first second of fall, or more precisely, 4.9 meters. Newton reasoned that gravitational attraction to the Earth must be diluted by distance. Does this mean the force of Earth's gravity would be 1/60th of the moon's distance? Figure 13.5. An apple falls 5 meters during its first second of fall when it is near Earth's surface. Newton asked how far the moon would fall in the same time if it were 60 times farther from the center of the Earth. No. As we shall soon see, the influence of gravity should be diluted to 1/60th of 1/60th, or to 1/60th squared. So in 1 second, the moon should fall 1/60th squared of 5 meters, which is 1.4 millimeters. Newton's calculation. Using geometry, Newton calculated how far the circle of the moon's orbit lies below the straight line distance the moon would otherwise travel in 1 second. His value turned out to be 1.4 millimeters, distance accepted today, as shown in figure 13.6, but he was unsure of the exact Earth-Moon distance and whether or not the correct distance to use was the distance between their centers. Figure 13.6. If the force that pulls apples off trees also pulls the moon into orbit, the circle of the moon's orbit should fall 1.4 millimeters during a point along the straight line where the moon would otherwise be 1 second later. Distance moon travels in 1 second. Without gravity, it should be here in 1 second. With gravity, it should fall to here in 1 second. Consider figure 13.6 carefully. At this time, he hadn't proved mathematically that the gravity of the spherical Earth and moon is the same as if all its mass were concentrated at its center. Because of this uncertainty, and also because of criticisms he had experienced in publishing earlier findings in optics, he placed his papers in a drawer where they remained for nearly 20 years. During this period, he laid the foundation and developed the field of geometrical optics, for which he first became famous. Newton finally returned to the moon problem at the prodding of his astronomer friend, Edmund Halley, of Halley's Comet fame. It wasn't until after Newton invented a new branch of mathematics, calculus, to prove his center of gravity hypothesis that he published what is one of the greatest achievements of the human mind, the law of universal gravitation. Newton generalized his moon finding to all objects and stated that all objects in the universe attract each other. Why doesn't the moon hit the Earth? 13.3. The falling Earth. Newton's theory of gravity confirmed the Copernican theory of the solar system. No longer was Earth considered to be the center of the universe. Earth was not even the center of the solar system. The sun occupies the center, and it became clear that Earth and the planets orbit the sun in the same way that the moon orbits Earth. The planets continually fall around the sun in closed paths. Why don't the planets crash into the sun? They don't, because the planets have tangential velocities as illustrated in figure 13.7. The tangential velocity of Earth about the sun allows it to fall around the sun rather than into it. Consider the concept of tangential velocity very carefully in our studies. What would happen if the tangential velocity of the planets were reduced to zero? The answer is simple enough. Their motion would be straight towards the sun, and they would indeed crash into it. Concept check. What theory of the solar system did Newton's theory of gravity confirm? Scientific truth and integrity, science, technology, and society. An advertiser who claims that 9 out of 10 doctors recommend the ingredient found in his or her advertised product may be telling the truth, but the implication being conveyed that 9 out of 10 doctors recommend the product itself may be quite false. An advertiser who claims that a certain brand of cooking oil will not soak through food is telling the truth. What the advertiser doesn't say is that no other brand of cooking oil soaked through foods either, at least not at ordinary temperatures and pressures. While the facts stated are true, the implications conveyed are not. There is a difference between truthfulness and integrity. Critical thinking. Do you think advertisers have a responsibility to be completely truthful about their products? Explain why or why not. 13.4 Newton's Law of Universal Gravitation. Newton did not discover gravity. Newton discovered that gravity is universal. Everything pulls on everything else in the universe in a way that involves only mass and distance. Newton's law of universal gravitation states that every object attracts every other object with a force. For any two objects, this force is directly proportional to the mass of each object. Newton discovered that gravity is universal. Everything pulls on everything else in the universe in a way that involves only mass and distance. The greater the masses, the greater the force of attraction between them. Newton also deduced that this force decreases as the square of the distance between the centers of the objects. The farther away the objects are from each other, the less the force of attraction between them. Notes: just as pi relates circumference and diameter for circles, g relates gravitational force to a combination of mass and distance. G, like pi, is a constant of proportionality. The law can be expressed as force is proportional to the product of mass 1 and mass 2 divided by the square of the distance, which in symbols is given here, where m1 is the mass of one object, m2 is the mass of the other, and d is the distance between their centers. Notes: just as sheet music guides a musician playing music, equation guide physics students to see how concepts are connected. Figure 13.8. The force of gravity between objects depends on the distance between their centers. The universal gravitation constant G. The law of universal gravitation can be expressed as an exact equation when a proportionality constant is introduced. In the equation for universal gravitation, the universal gravitation constant G describes the strength of gravity. Then, the equation is F equals G times the ratio of m1 and m2 squared divided by the distance squared. In words, the force of gravity between two objects is found by multiplying their masses, dividing by the square of the distances between their centers, and then multiplying this by g. The magnitude of g is given by the magnitude of the force between two masses 1 kilograms each, 1 meter apart. For these masses, this is an extremely weak force. The units of g are such as to make the force come out in newtons. In scientific notation, it's 6.67 times 10 to the negative 11. And the units are Newton meter squared divided by kilogram squared. Measuring G. G was first measured 150 years after Newton's discovery of universal gravitation by the English physicist Henry Cavendish. Cavendish accomplished this by measuring the tiny force between lead masses with an extremely sensitive torsion balance. A simpler method was later developed by Philip von Jolly, who attached a spherical flask of mercury in one arm of a sensitive balance, as shown in figure 13.9. After the balance was put in equilibrium, a 6-ton lead sphere was rolled beneath the mercury flask. The flask was pulled slightly downward. In effect, the gravitational force F between the lead mass and the mercury was equal to the weight that had to be placed on the opposite end of the balance to restore equilibrium. Since the quantities F, M1, M2, and D were all known, the value of G could be calculated. So start with the basic equation, force equals G times M1, M2 divided by D squared. Rearrange the equation and solve for G. Figure 13.9, Philip von Jolly developed a method of measuring the gravitational attraction between two masses. Now solve for G, and you see that when you plug in the values that you get, G is 6.67 times 10 to the negative 11, and it's very, very small number. And don't forget the units, N, M squared over kg squared. The value of G tells us that the force of gravity is a very weak force. It is the weakest of the presently known four fundamental forces. The other three are the electromagnetic force and two kinds of nuclear forces. We sense gravitation only when masses like that of the Earth are involved. The force of attraction between you and a classmate is too weak to notice, but it's there. The force of attraction between you and Earth, however, is easy to notice. It is your weight in addition to your mass. Your weight also depends on your distance from the center of the Earth. At the top of a mountain, like the one shown in figure 13.10, your mass is the same as it is anywhere else, but your weight is slightly less than at ground level. Your weight is less because your distance from the center of Earth is greater. Interestingly, Cavendish's first experiment of G was called the weighing the Earth experiment, because once the value of G was known, the mass of Earth was easily calculated. The force that Earth exerts on a mass of 1 kilogram at its surface is 10 newtons. The distance between the 1 kilogram mass and the center of the Earth radius figure 13.4. Your weight is less at the top of a mountain because you are farther from the center of the Earth. Therefore, from F equals G times M1, M2 divided by D squared, where M1 is the mass of Earth, rearrange for M1 and follow through, plug in, and you get the mass of Earth, M1, is 6 times 10 to the 24th kilograms. What did Newton discover about gravity? Study the calculation very carefully. I'll leave it on for a few seconds. Figure 13.11, when G was first measured in the 1700s, newspapers everywhere announced the discovery as one that measured the mass of planet Earth. This was particularly exciting at a time when a great portion of Earth's surface was still undiscovered. Do the math. How can you express very large and very small numbers in scientific notation? Very large and very small numbers are conveniently expressed in a mathematical format called scientific notation. An example of a large number is the equatorial radius of Earth, which is 6,370,000 meters. This number can be obtained by multiplying 6.37 times 10 and again by 10 and so on until 10 has been used as a multiplier 6 times. So 6,370,000 can be written as 6.37 times 10 to the 6th. That's 6.37 million meters. 1,000 million is a billion, 10 to the 9th. To better comprehend the size of a billion meters is slightly more than the Earth moon distance. 1 billion kilograms is the mass of about 120 Eiffel Towers. 1 billion Earths would equal the mass of about 3 suns. 1 billion seconds is 31.7 years. 1 billion minutes is 1903 years. 1 billion years ago, there were no humans on Earth. 1 billion people live in China. 1 billion atoms make up the dot over the I. Small numbers are expressed in scientific notation by dividing by 10 successive times. A millimeter, mm, is 1 over 1,000 meters, or 1 meter divided by 10 3 times. In scientific notation, 1 millimeter equals 10 to the negative 3 meters. The gravitational constant g is a very small number. By dividing 6.6726 by 10 11 times and rounding off, it is 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. 13.5. Gravity and distance, the inverse square law. We can understand how gravity is reduced with distance by considering an imaginary butter gun used in a busy restaurant for buttering toast. Imagine melted butter sprayed through a square opening in a screen. The opening is exactly the size of a piece of square toast. And imagine that a spurt from the gun deposits an even layer of butter 1 millimeter thick. Consider the consequences of holding the toast twice as far from the butter gun. You can see in figure 13.12 that the butter would spread out for twice the distance and would cover twice as much toast vertically and twice as much toast horizontally. A little thought will show that the butter would now spread out to cover 4 pieces of toast. Figure 13.12. Butter sprays travel outward from the nozzle of a butter gun in straight lines. Like gravity, the strength of the spray obeys an inverse square law. How thick will the butter be on each piece of toast? Since it has been diluted to cover 4 times as much area, its thickness will be 1/4 as much, or 0.25 millimeters. Note what has happened. When the butter gets twice as far from the gun, it is only 1/4 as thick. More thought will show that if it gets 3 times as far, it will spread out to cover 3 times 3, or 9 pieces of toast. How thick will the butter be then? Can you see that it will be 1/9 as thick? And can you see that 1/9 is the inverse square of 3? The inverse of 3 is simply 1/3. The inverse square of 3 is 1/3 squared, or 1/9. When a quantity varies as the inverse square of its distance from its source, it follows an inverse square law. Gravity decreases according to the inverse square law. The force of gravity weakens as the square of distance. This law applies not only to the spreading of butter from a butter gun and the weakening of gravity with distance, but in all cases where the effect from a localized source spreads evenly throughout the surrounding space. More examples of light, radiation, and sound. Figure 13.13 shows how the greater the distance from Earth's center, the less an object will weigh. An apple that weighs 1 Newton at Earth's surface weighs only 0.25 newtons when located twice as far from the Earth's center, because the pull of gravity is only 1/3 as strong. When it is 3 times as far, it weighs only 19 as much, or 0.11 newtons. If your little sister weighs 300 newtons at sea level, She will only weigh 299 newtons atop Mount Everest. Notes: saying that F is inversely proportional to the distance of D means, for example, that if D increases by a factor of 3, F decreases by a factor of 9. Figure 1313, gravitational force is plotted in red versus the distance from Earth's center. Study it closely. But no matter how great the distance, Earth's gravity does not drop to zero. Even if you were transported to the far reaches of the universe, the gravitational influence of Earth would be with you. It may be overwhelmed by the gravitational influences of nearer and more massive objects, but it is there. The gravitational influence of every object, however small or far away, is exerted through all space. That's impressive. Notes: myth: there is no gravity in space. Fact: gravity is everywhere. Concept check. How does force of gravity change with distance? Think. Suppose that an apple at the top of a tree is pulled by Earth's gravity with a force of 1 Newton. If the tree were twice as tall, would the force of gravity on the apple be only 1/4 as strong? Explain your answer. No, because the twice as tall apple tree is not twice as far from Earth's center. The taller tree would have to have a height equal to the radius of the Earth, or 6,370 kilometers, before the weight of the apple would reduce to 1/4 Newton. Before its weight decreases by 1%, an apple or any object must be raised 32 kilometers, nearly 4 times the height of Mount Everest, the tallest mountain in the world. So, as a practical matter, we disregard the effects of everyday changes in elevation. 13.6 Gravitational Field. We know Earth and the Moon pull on each other. This is action at a distance because both bodies interact with each other without being in contact. But we can look at this in a different way. We can regard the Moon as in contact with the gravitational field of Earth. A gravitational field occupies the space surrounding a massive body. A gravitational field is an example of a force field. For any mass in the field, space experiences a force. Notes: Earth has a gravitational field and a magnetic field. Earth can be thought of as being surrounded by a gravitational field that interacts with objects and causes them to experience gravitational forces. It is common to think of rockets and distant space probes being influenced by the gravitational field at their locations in space rather than by Earth and other planets or stars acting from distances. The force field concept plays an in-between role in our thinking about the forces between different masses. A more familiar force field is the magnetic field of a magnet. Look ahead to figure 36.4. Iron filings sprinkled over a sheet of paper on top of a magnet reveal the shape of the magnet's magnetic field. The pattern of filing shows the strength and direction of the magnetic field at different locations around the magnet. Where the filings are close together, the field is strong. The direction of the filing shows the direction of the field at each point. Planet Earth is a giant magnet, and like all magnets, is surrounded by a magnetic field. Evidence of the field is easily seen by the orientation of a magnetic compass. Field lines can also represent the pattern of Earth's gravitational field. Like the iron filings around a magnet, the field lines are closer together where the gravitational field is stronger. Figure 36.4. Iron filings trace out a pattern of magnetic field lines in the space surrounding the magnet. You can see the north and south, and then the field lines. The arrows in figure 13.14 show the field direction. A particle, astronaut, spaceship, or any mass in the vicinity of Earth will be accelerated in the direction of the field lines at that location. The strength of the Earth's gravitational field, like the strength of its forces on the object, follows the inverse square law. Earth's gravitational field is strongest near Earth's surface and weaker at greater distances from Earth. Figure 13.14, field lines represent the gravitational field about Earth. An example of a force field is the one that surrounds electrical charges. The electric field, which we shall study in Chapter 33. In Chapter 36, we'll learn how magnets align with magnetic fields of Earth to become compasses. In Chapter 11, we've already learned how the Moon similarly aligns with Earth's gravitational field, resulting in the same side of the Moon facing us. Force fields have far-reaching effects. Concept check. What kind of field surrounds Earth and causes objects to experience gravitational forces? Astronaut, physics on the job. 3, 2, 1. The space shuttle leaves Earth with its crew of 7 astronauts. An astronaut pilot or works on a spacecraft or conducts experiments during spaceflight. Astronauts understand how the force of gravity will change throughout their trip. Here's a spacewalk from the space station or space shuttle. They apply physics to control the direction of a spacecraft, conduct experiments in space, and move outside the spacecraft. Astronauts usually have flight experience along with degrees in scientific disciplines such as physics or chemistry. You'll see that the gravity on the space station is actually not terribly different from what it is on Earth, but they are in free fall. They still have gravity, but they don't have the support force. The United States astronaut program is managed by the National Aeronautics and Space Administration, called NASA. The gravity on the International Space Station is about 90% of what it is on Earth. But remember, the astronauts, the International Space Station, the Moon, etc., are orbiting the Earth because they are in free fall and they keep missing the Earth. But they are in free fall, so there's no support force. They still have their weight, but no support force. So they are seemingly weightless. 13.7, gravitational field inside a planet. The gravitational field of Earth exists inside Earth as well as outside. To investigate the gravitational field beneath the surface, imagine a hole drilled completely through Earth. Say that the North Pole to the South Pole, as shown in figure 13.15. Forget about impracticalities such as lava and high temperatures, and consider the kind of motion you would undergo if you fell into such a hole. If you started at the North Pole end, you'd fall and gain speed all the way down to the center, and then overshoot and lose speed all the way to the South Pole. You'd gain speed moving towards the center and lose speed moving away from the center. Figure 13:15, as you fall faster and faster into a hole bored through Earth, your acceleration diminishes because the pull of mass above you partly cancels the pull below. If you stepped into a hole bored completely through Earth and made no attempt to grab the edges at either end, what kind of motion would you experience? You would oscillate back and forth, approximately simple harmonic motion. A round trip would take nearly 90 minutes. Interestingly enough, we would see in the next chapter that an Earth satellite in close orbit about Earth also takes the same 90 minutes to make a complete round trip. This is not a coincidence, but a feature of simple harmonic motion from chapter 25. Without air drag, the trip would take nearly 45 minutes. If you failed to grab the edge, you'd fall back towards the center, overshoot, and return to the North Pole in the same amount of time. Suppose you had some way to measure your acceleration during this trip. At the beginning of the fall, your acceleration would be g, but you'd find acceleration progressively decreasing as you continue towards the center of the Earth. Why? Because as you are being pulled downward toward Earth's center, you're also being pulled upward by the part of the Earth that is above you. In fact, as illustrated in figure 13:16, when you get to the center of the Earth, the pull down is balanced by the pull up. You are pulled in every direction equally, so the net force on you is zero. Figure 13:16, in a cavity at the center of the Earth, your weight would be zero because you would be pulled equally by gravity in all directions. Curious. There is no acceleration as you whiz with maximum speed past the center of Earth. The gravitational field of Earth at its center is zero. Concept check. Describe the gravitational field of Earth at its center. 13.8, weight and weightlessness. The force of gravity, like any force, causes acceleration. Objects under the influence of gravity are pulled toward each other and accelerate, as long as nothing prevents the acceleration. We are almost always in contact with Earth. For this reason, we think of gravity primarily as something that presses up against Earth, rather than something that accelerates us. Force against Earth is the sensation we interpret as weight. Stand on a bathroom scale that is supported by a stationary floor. The gravitational force between you and Earth pulls you against the supporting floor and scale. By Newton's third law, the floor and scale in turn push upward on you. Located between you and the supporting floor is a spring-like gauge inside the bathroom scale. This pair of forces compress the gauge. The weight reading on the scale is linked to the amount of compression. If you repeat this weighing procedure in a moving elevator, as shown in figure 13:17, you would find your weight reading would vary, not during steady motion, but during accelerated motion. If the elevator accelerated upward, the bathroom scale and floor would push harder against your feet, and the gauge inside the scale would be compressed even more. The scale would show an increase in your weight. Figure 13:17, the sensation of weight is equal to the force that you exert against the supporting floor. Consider this figure very carefully. If the elevator accelerated downward, the support force of the floor would be less and the scale would show a decrease in your weight. If the elevator cable broke and the elevator fell freely, the scale reading would register 0. According to the scale, you would be weightless and you would feel weightless, for your insides would no longer be supported by your legs and pelvic region. Your organs would respond as though gravity were absent. But gravity is not absent. So would you really be weightless? The answer to this question depends on your definition of weight. Rather than define your weight as the force of gravity that acts on you, it is more practical to define weight as the force you exert against a supporting floor or weighing scales. According to this definition, you are as heavy as you feel. Thus, the condition of weightlessness is not the absence of gravity. Rather, it is the absence of a support force, that queasy feeling you get when you are in a car that seems to leave the road momentarily when it goes over a hump, or worse, off a cliff, as shown in figure 1318, is not the absence of gravity. It is the absence of a support force. Astronauts in orbit are without a support force and are in sustained state of weightlessness. Astronauts sometimes experience space sickness until they get used to a state of sustained weightlessness. Figure 1318, both people are without a support force and therefore experience weightlessness. Consider the concept very carefully. Weightlessness or zero gravity. For future space travelers, however, need not be subjected to weightlessness. As mentioned in the previous chapter, lazily rotating giant wheels will likely supplant today's non-rotating space habitats. Rotation effectively supplies a support force and nicely provides weight. Concept check. What sensation do we interpret as weight? 13.9 Ocean Tides. Seafaring people have always known there was a connection between the ocean tides and the moon, but no one could offer a satisfactory theory to explain why there are 2 high tides per day. You may have noticed this rise and fall of seawater as shown in figure 1319 on visits to the ocean. Newton showed that the ocean tides are caused by differences in the gravitational pull of the moon on opposite sides of Earth. Figure 1319, the ocean tides are caused by differences in the gravitational pull of the moon on opposite sides of the Earth. And in some areas of the Earth, the difference between low and high tide is dramatic. The moon's attraction is stronger on Earth's ocean closer to the moon and weaker on the oceans farther from the moon because the gravitational force is weaker with increased distance. This difference in pull across Earth slightly elongates it. Through a similar effect of Earth on the moon is slightly elongated too. Rather than being spherical, both Earth and Moon are pulled into a shape that slightly resembles a football. For Earth, the elongation is mainly in the most pliable part, the oceans. The ocean bulge out about 1 meter on average on opposite sides of the Earth. Because the Earth spins once per day, a fixed point on Earth passes beneath both of these bulges each day, as illustrated in figure 1320. Figure 1320, the 2 tidal bulges remain relatively fixed with respect to the moon while Earth spins daily beneath them. Very interesting. This produces 2 sets of ocean tides per day, 2 high tides and 2 low tides. Factors affecting ocean tides. The sun also contributes to ocean tides. About half as much as the moon, even though its pull on Earth is 180 times greater than the moon's pull on Earth. Then, why aren't tides due to the sun 180 times greater than lunar tides? Because the difference in gravitational pull by the sun on opposite sides of the Earth is very small, only about 0.0717% compared to 6.7 for the moon's gravitation. Figure 13.21 illustrates the configuration of the sun, Earth, and moon that produces spring tides. Figure 13.21, when the sun, the moon, and Earth are aligned, spring tides occur. You can see how the Earth, when it's going to rotate, is going to pass under the bulges twice a day. A spring tide is a high or low tide that occurs when the sun, Earth, and moon are all lined up. The tides due to the sun and the moon coincide, making the high tides higher than average and the low tides lower than average. Since tides occur at the time of a new or full moon and have nothing to do with the spring season, a neap tide occurs when the moon is halfway between the new moon and a full moon in either direction, as illustrated in figure 13.22. The pulls of the moon and the sun are perpendicular to each other. As a result, the solar and lunar tides do not overlap, so the high tides are not as high and the low tides are not as low. Figure 13.22. When the attraction of the sun and the moon are at right angles to each other at the time of a half moon, neap tide occurs. Other types of tides. Because much of the Earth's interior is deformable, we have Earth's tides, though they are less pronounced than ocean tides. Twice each day, the solid surface of Earth rises and falls as much as 1/4 meter. There are also atmospheric tides, which affect the intensity of cosmic rays that reach the Earth's surface. These rays, affected even more strongly by Earth's magnetic field, induce subtle changes in living things. Ocean tides, Earth tides, and atmospheric tides are greatest when the sun, Earth, and moon are aligned. At the time of a full or new moon, the tilt of the Earth's axis interfering land masses, friction with the ocean bottom, and other factors complicate tidal motions. Figure 13.23 illustrates the effect of the tilt of Earth's axis on tides. Although the moon produces considerable tides in Earth's oceans, which are thousands of kilometers across, it produces scarcely any tides in a lake. That's because no part of the lake is significantly closer to the moon than any other part. This means there is no significant difference in the moon's pull on different parts of the lake. Notes: atmospheric tides influence the number of cosmic rays reaching Earth's surface. Like ocean tides, atmospheric tides are greatest when the moon, sun, and Earth are aligned. Figure 13.23. Earth's tilt causes the two daily high tides to be unequal. Similarly, any tides in the fluids of your body caused by the moon are negligible. You're not tall enough for tides. What microtides the moon may produce in your body are only about 1/200th the tides produced by a 1 kilogram melon held 1 meter above your head. Tides are fascinating. What causes ocean tides? Power production, science, technology, and society. Power plants that run on tidal power are numerous throughout the world. The first modern tidal power plant in North America has been operating since 1984 in Nova Scotia, Canada. A dam across an estuary gets its power from the rising and falling of the daily ocean tide. First, the water is higher on one side of the dam and is maintained at about 1.6 meters higher than the lower side. Water then flows through a series of gates to the lower side, turning a huge turbine in the process. When the tide changes, the flow of water is in the reverse direction, again turning the turbine. The dam produces more than 20 megawatts of power, enough to meet the electricity needs for 4,500 homes. The largest tidal power plant produces 240 megawatts of electric power in Brittany, France. Watch for the growth of this green technology. What are the advantages of using ocean tides to produce electricity? Critical thinking. 1984, North America's first and only tidal generating station was built in Annapolis Royal, Nova Scotia. Still in operation, when running, the plant produces about 20 megawatts, enough to power about 6,000 homes. 13.10 Black holes. There are two main processes going on continuously in stars like our Sun. Figure 13.24 illustrates these two processes. One process is gravitation, which tends to crush all solar material towards the center. The other process is thermonuclear fusion, consisting of reactions similar to those in a hydrogen bomb. These hydrogen bomb-like reactions tend to blow solar material outward. When the process of gravitation and thermonuclear fusion balance each other out, the result is the sun of a given size. Figure 13.24, the size of the sun is the result of a tug of war between two opposing processes, nuclear fusion and gravitational contraction. Formation of black holes. If the fusion rate increases, the sun will get hotter and bigger. If the fusion rate decreases, the sun will get cooler and smaller. What will happen when the sun runs out of fusion fuel, hydrogen? The answer is gravitation will dominate and the sun will start to collapse. For our sun, this collapse will ignite the nuclear ashes of fusion, helium, and fuse them into carbon. During this fusion process, the sun will expand to become the type of star known as a red giant. It will be so big that it will extend beyond Earth's orbit and swallow Earth. Fortunately, this won't take place until some 5 billion years from now, when the helium is all burned and the red giant will collapse and die. It will no longer give off heat and light. It will then be the type of star called a black dwarf, a cool cinder among billions of others. The story is a bit different for stars more massive than the sun. For a heavy star, one that is at least 2 to 3 times more massive than our sun, once the flame of thermonuclear fusion is extinguished, gravitational collapse takes over. And it doesn't stop. The star not only caves in on itself, but the atoms that compose the stellar material also cave in on themselves until there are no empty spaces. According to theory, the collapse never stops and the density becomes literally infinite. Gravitation near these shrunken configurations, which are called black holes, is so enormous that nothing can get back out. Even light cannot escape a black hole. They have crushed themselves out of visible existence. Gravitational field near black holes. Perhaps surprisingly, a black hole is no more massive than the star from which it collapsed. When a massive star collapses into a black hole, there is no change in the gravitational field at any point beyond the original radius of the star. The gravitational field near the black hole may be enormous, but, as shown in figure 13.25, the field beyond the original radius of the star is no different after collapse than before. Figure 13.25. The gravitational field strength near a giant star that collapses to become a black hole is the same before collapse left and after collapse right. Study this very carefully. The amount of mass has not changed, so there is no change in the field at any point beyond this distance. Black holes will be formidable only to future astronauts who venture too close. Contrary to stories about black holes, they're non-aggressive and don't reach out to swallow innocence at a distance. Their gravitational fields are no stronger than the original fields about the stars before their collapse. Except at distances smaller than the radius of the original star, black holes shouldn't worry future astronauts unless they get too close. Effects of black holes. Although black holes can't be seen, their effects can be. Many stars in the sky occur as binaries, pairs that orbit each other. Sometimes only one star of a binary pair is seen. Matter streams from this visible star towards its invisible companion, emitting X-rays as it accelerates towards the nothingness that is probably a black hole. And near the centers of most galaxies are immensely massive yet very small centers of force that cause stars near them to speed around in tight orbits. These black holes, if that's what they are more massive than a million suns. What happens to the gravitational field of a star that has collapsed into a black hole? Figure 1326, the gravitational field around a black hole is usually represented as a warped two-dimensional surface. Universal gravitation. We all know that Earth is round, but why is Earth round? It is round because of gravitation. Since everything attracts everything else, Earth had attracted itself together before it became solid. Any corners of Earth have been pulled in so that Earth is a giant sphere. The sun, the moon, the Earth are all fairly spherical because they have to be rotational effects make them somewhat wider at their equators. Figure 1327 shows how gravity played a role in the formation of the solar system. A slightly rotating ball of stellar gas, which is illustrated in figure 1327a, contracted due to mutual gravitation, which is shown in figure 1327b. 1327. Gravity played an important role in the formation of the solar system. Here you have A, B, and C. To conserve angular momentum, the rotational speed of the ball of gas increased. The increased momentum of the individual particles and clusters of particles caused them to sweep into wider paths about the rotational axis, producing an overall disk shape as shown in figure 13.27c. The greater surface area of the disk promoted cooling and clusters of swirling matter, the birthplace of planets. Perturbations in the solar system. If everything pulls on everything else, then the planets must pull on each other. The net force that controls Jupiter, for example, is not just from the Sun, but from the other planets also. Their effect is small compared with the pull of the more massive Sun, but it still shows. Planetary rings link to astronomy. 4 planets in the solar system have a system of planetary rings. The rings of Saturn were brought vividly to life in 2004 by the Cassini-Huygens space probe. Tidal forces may have caused the formation of these rings. A satellite experiences competing forces, the tidal forces that tend to tear it apart, and the self-gravitation that holds it together. Early in the life of the solar system, Saturn and other outer planets may have had one or more moons orbiting too close to the planet's surface. Powerful tidal forces could have stretched them and torn them apart. During billions of years, fragments could have separated into billions and still smaller pieces, spreading out to form the beautiful rings we see today. Our moon is sufficiently far away to resist this tidal disintegration, but if it were to come too close, within a few hundred kilometers of Earth, the increased tidal forces would tear the moon apart. Then Earth, like Saturn, Jupiter, Uranus, and Neptune, would have a system of planetary rings. When the planet Saturn is near Jupiter, for example, its pull disturbs the otherwise smooth path of Jupiter. Both planets deviate from their normal orbits. The deviation of an orbiting object from its path around a center of force caused by the action of an additional center of force is called perturbation. Until the middle of the last century, astronomers were puzzled by unexplained perturbations of the planet Uranus. Even when the influences of the other planets were taken into account, Uranus was behaving strangely. Either the law of gravitation was failing at this great distance from the Sun, or some unknown influence, such as another planet, was perturbing Uranus. The source of Uranus's perturbations was uncovered in 1845 and 1846 by 2 astronomers, John Adams in England and Urbain Le Verrier in France. With only pencil and paper and the application of Newton's law of gravitation, both astronomers independently arrived at the same conclusion. A disturbing body beyond the orbit of Uranus was the culprit. They sent letters to their local observatories with instructions to search a certain part of the sky. The request by Adams was delayed by misunderstandings at Greenwich, England, but Le Verrier's request to the director of the Berlin Observatory was heeded right away. The planet Neptune was discovered within half hour. Subsequently, tracking of the orbits of both Uranus and Neptune led to the prediction of another massive body beyond Neptune. In 1930, at Lowell Observatory in Arizona, Pluto was discovered. Whatever you may have learned in your early schooling, astronomers now regard Pluto as a dwarf planet and not a full-fledged planet. Pluto takes 248 years to make a single revolution about the Sun, so no one will see it in its discovered position again until the year 2178. The expanding universe. The shapes of distant galaxies provide further evidence that the law of gravity applies to larger distances. According to current scientific understanding, the universe originated and grew from the explosion of a primordial fireball some 13.7 billion years ago. This is the Big Bang theory of the origin of the universe. All the matter of the universe was hurled outward from this event and continues in an outward expansion. Evidence for this includes precise measurements of the earliest remnants of the Big Bang, its cosmic microwave background. More recent evidence suggests the universe is not only expanding, but accelerating outward. It is pushed by an anti-gravity dark energy that makes up an estimated 73% of the universe. 23% of the universe is composed of the yet-to-be-discovered particles of exotic dark matter. Ordinary matter, the stuff of stars, cabbages, and kings, makes up only 4%. The concepts of dark matter and dark energy will continue to inspire exciting research throughout this century. They may hold clues to how the cosmos began and where it is headed, and may be the key to understanding the fate of the universe. Astronomers, physics on the job. Astronomers study the physics of nature's extremes, from the coldness of empty space to the fiery hotness of exploding stars, and from tiny elementary particles of matter to the vastness of the universe itself. Astronomers work mainly for university and government observatories. Whereas most of the efforts of early astronomers were in cataloging objects in the sky, astronomers today employ much physics as they study the history of the universe from the Big Bang to the present and seek to understand black holes, dark matter, and dark energy. It can truly be said that astronomers are far-out people. Our present view of the universe has progressed appreciably beyond the universe as Newton perceived it. Newton's impact on science. Few theories have affected science and civilization as much as Newton's theory of gravity. The successes of Newton's ideas ushered in the Age of Reason, or Century of Enlightenment. Newton demonstrated that by observation and reason, people could uncover the workings of the physical universe. How profound it is that all the moons and planets and stars and galaxies have such a beautifully simple rule to govern them, namely F equals G times M1, M2 divided by D squared. The formulation of the law of universal gravitation is one of the major reasons for the success in science that followed, for it provided hope that other phenomena of the world might also be described by equally simple and universal laws. This hope nurtured the thinking of many scientists, artists, writers, and philosophers of the 1700s. Scientists' usage of the term theory differs from common usage. The theory of gravity, for example, is universally accepted by scientists based on the preponderance of evidence and the success of the model. The term theory does not imply fundamental doubts about the phenomenon's existence. Discover which hand is bigger. Hold your hands outstretched, one twice as far from your eyes as the other. Make a casual judgment about which hand looks bigger. Now overlap your hands slightly and carefully view them with one eye closed. Think, why does one hand appear bigger than the other? One of these was the English philosopher John Locke, who argued that observation and reason, as demonstrated by Newton, should be our best judge and guide in all things. Your author wonders about readers of this book who will continue in their studies of physics and help to decipher the nature of dark matter, dark energy, and other wonders of the universe yet to be discovered. Locke urged that all of nature and even society should be searched to discover any natural laws that might exist. Using Newtonian physics as a model of reason, Locke and his followers modeled a system of government that found adherents in the 13 British colonies across the Atlantic. These ideals culminated in the Declaration of Independence and the Constitution of the United States of America. How did the formulation of the laws of universal gravitation affect science? Summary: Universal gravitation. Newton reasoned that the moon is falling towards the Earth for the same reason an apple falls from a tree. They are both pulled by Earth's gravity. The moon is actually falling towards Earth, but has great enough tangential velocity to avoid hitting Earth. Newton's theory of gravity confirmed the Copernican theory of the solar system. Newton discovered that gravity is universal. Gravity decreases according to the inverse square law. Earth can be thought of as being surrounded by a gravitational field that causes objects to experience gravitational forces. The gravitational field of Earth at its center is zero. Force against Earth is the sensation we interpret as weight. The ocean tides are caused by differences in the gravitational pull of the moon on opposite sides of Earth. When a massive star collapses into a black hole, there is no change in the gravitational field at any point beyond the original radius of the star. The formulation of the law of universal gravitation provided hope that other phenomena of the world might also be described by equally simple and universal laws.